My name is Noah Chiwanuka. I'm a medical doctor by profession and an infectious disease epidemiologist with a lot of bias in epidemiology and biostatistics. I'm an associate professor of epidemiology and biostatistics. And this time round, we are going to be talking about the subject of inferential statistics, estimation, and hypothesis testing. The learning objectives for this subject, at the end of the topic, a student should be able to distinguish between a type 1 and type 2 error. Should be able to formulate an hypothesis and go through the steps required to test that hypothesis, whether it's a difference of means or difference of proportions, and should be able to come up with a correct conclusion, apply a test statistic, determine the critical value, estimate the p-value, and decide whether to reject or fail to reject the null hypothesis. I want to emphasize from the beginning that when you are doing hypothesis testing, the onus of proof that we want to provide to the scientific community is what lies on the alternative hypothesis. In other words, what we want to prove is always on alternative hypothesis. But then we set the null hypothesis, which is the hypothesis that negates or cancels the alternative hypothesis, or the hypothesis of no effect. So there are two things that we do in hypothesis testing that I must emphasize from the beginning. We either reject the null hypothesis or fail to reject the null hypothesis. We either reject or fail to reject the null hypothesis. So what is inferential statistics? Inferential statistics, the word inferential comes from inference. This inferential statistics refers to the statistical methods that we apply to make a conclusion or an inference from the figures or the findings we get in a sample and generalize them or apply them to the reference population from which the sample came. And in the coming slides, we are going to illustrate this diagrammatically. When we are studying any parameter, anything in the population, we actually can't study the whole population. Assuming we are studying the population of Uganda, we cannot study the whole population for many reasons. Logistically cumbersome, it's very expensive, it takes more time, and if you can get the same conclusions from a sample, why then would you bother actually studying the whole population, which is going to take forever? So what we practically do is we have a reference population, as you can see on the slide. Then we take a sample from the reference population, and then we study that sample. And from the sample, we estimate what we call a sample statistic. And we use that sample statistic to see how well the statistic from a sample represents the parameter in the population. So inferential statistics lies between the comparison of a sample statistic to the population parameter. A measure that is derived from the entire population is known as a population parameter. It could be a population mean, it could be a population proportion, it could be a difference of population means, it could be a difference of population proportions. But as long as that measure is based on the entire population, it is known in statistics as a parameter. Now we get a measure from a sample, a similar measure from a sample that was derived or collected from the population, and that measure from a sample is known as a statistic. So in inferential statistics, we want to compare the statistic from a sample to the parameter in the population that the sample represents. Another way of demonstrating it or illustrating it is what you can see on the slide. The parameter is based on the entire population. Then we take a sample based on a given sampling distribution and we obtain a sample. Then we take measures from the sample, and these measures are known as statistics. Then we want to see how does the sample statistic compare to the population parameter. And this arrow here, how well does the sample statistic compare to the population parameter, is what is known as inferential statistics or statistical inference. And we do two things that we are going to demonstrate later on. So in summary, so far, what have we covered? We have seen that inferential statistics is about making judgments on how well the sample statistic represents the population parameter. You can also say inferential statistics is about making judgments on the probability of an observed difference between the groups and how that is dependable on given circumstances. And so we use a sample statistic and make conclusions on the unmeasured population parameter. The judgments that we make in inferential statistics must be rational, not based on gut feeling. They are rational, they are based on mathematical measurements and calculations to be able to draw a conclusion on whether the sample statistic represents the population parameter well or it is off the expected population parameter using probabilities and making some assumptions. We're now going to move on to estimation. As we've already highlighted, we take a sample from the population and measure a statistic, get a statistic out of the sample. So we do estimate both the sample statistic and the population parameter. There are two ways of estimating. There is what we call the point estimate and the interval estimate. In point estimate, we estimate the population parameter to the dot. For example, if the population parameter is a mean of adolescent girls' weight, and their weight, the mean weight, the true mean weight of the population is, for example, 42.5 kilograms. In the point estimate, we want to see whether the statistic in a sample, the mean weight in a sample of adolescent girls is also exactly 42.8 or 42.5. That is point estimation. Estimating using the statistic to estimate the parameter exactly as the parameter is. But as you know, life is not generally point estimate. There are variabilities. Things vary depending on how you get the sample, what sample you get, what method you used. So in reality, we really don't do point estimate. In reality, we do interval estimation. And what does interval estimation mean? It means that we do estimate the parameter, but instead of estimating it to the dot, we give a degree of variability around the point estimate that we are comfortable, so that when our statistic lies within that degree of variability, then we can say it is as good as the point estimate. So this is what interval estimate is all about. It is a point estimate plus a degree of variability around the point estimate. And this degree of variability is two ways. It is less than the point estimate and greater than the point estimate. And it has to be in equal measures. The number of measures you go below the point estimate are exactly the same as what you go above the point estimate to create an even variability around the point estimate, so that below it you have the same steps as above it. Now, for us to do interval estimation, there are some measures that we use. One of it is the standard error of the mean. And let us define what the standard error of the mean is. And to do this, let's take a step back and go to the earlier lecture that you had about measures of central tendency and measures of dispersion. You remember that in measures of central tendency, you covered the mean, the mode, and the median. And the mean is the average, and there was a standard deviation around it. And the mode is what occurs frequently in the sample, and the median is the middle observation in a sample that is arranged chronologically. And for the median, we put also a variability known as the interquartile range. You do remember that. And in the measures of dispersion, we had the variance. And remember that the variance is estimated by getting each observation, x sub I, minus its mean x bar squared divided by n minus 1, and that gives us the variance. Then when we take the square root of the variance, it gives us the standard deviation. The standard deviation represents the variability of each observation around its group mean. Because if we can demonstrate on the board, the way we estimated the variance was xi, each observation, minus x bar, its group mean, squared divided by n minus 1, and this was giving us the variance s squared if it is for a sample, or sigma squared if it is for the population. You can clearly see that each observation is subtracted from its mean, and then it is standardized using these degrees of freedom n minus 1. And so once we get the standard, the variance, and take a square root of it, we end up getting the standard deviation. So the standard deviation represents the variability of the individual observation around its group mean. And keep that in mind as we go to what the standard error of the mean is. Now, assume that you have samples that range from sample 1 to sample 1, N1, all the way down to N10. These are 10 samples, and they are equal in size. So each one of them, we calculate, we have observations xi all the way to xn, the last observation. Then we calculate a mean. This will be x bar 1. That is the mean for sample 1. The one for 10 will be x bar 10. That's the mean for sample 10. How each observation varies around its mean gives us the variance, which in turn gives us the standard deviation. And we've just seen that. Now, if you get these means, now you go to this column of means. We have mean 1 for sample 1, mean 2 for sample 2, all the way to mean 10 for sample 10. If you get these means and take the average of the means, summation of the means from mean 1, sample 1 to mean 10, if you add these means and divide them by their number, which is in this case will be 10, summation of means from mean 1, sample 1 to sample 10, you sum these means and divide them by 10, you end up getting the mean of the means. Okay? This is now, it is not the mean of one group, because x bar is the mean, x bar 1 is the mean of group 1, x bar 10 is the mean of group 10. If we take these means, add them together, divide them by the total number of the samples, which is 10, then we get the average of the means, which is a mean of means. Now, for illustration's sake, assume that the mean of means is here in this place where you see the green. This is the mean of means. It will show that some, and assuming also that they increase in order going downwards. So this being the smallest and this being the largest. you will see clearly that some means of some groups are less than the mean of means. Some are greater than the mean of means. Some of them, like for N5, may be equal to the mean of means. So even these group means also vary around the mean of means. Just like the individual observations vary around their group mean. So the variation of the individual observations around their group mean gives us the standard deviation. But the variation of the group mean around the mean of means gives us the standard error of the mean. So the standard error of the mean represents the variation or variability of the mean of a given group mean around the mean of means. And that parameter or that figure is very, very important because it helps us to determine the variability and therefore to estimate our interval around the point estimator. So as can be seen on the slides, the standard error of the mean represents the variability of the sample mean around the grand mean or the mean of means. And it is mathematically represented by sigma over root n. As you can see on the slide, standard error of the mean is equal to sigma or s, if you are using a sample, over the square root of the sample size. And what does this show us? That for any given fixed standard deviation sigma or SD, if the sample size increases, which is the denominator, the sampling error of the mean decreases because you are holding this one constant and increasing the sample size. So the denominator is increasing without the numerator increasing, so the sampling error decreases. And if we go back to our illustration on the board, when you have a big standard error of the mean, if the standard error of the mean is, for example, 0.2, it means that around the mean of means, the expected values will probably be around here. Whereas if the standard error of the mean is 0.4, it means that the mean of means vary wider around the group means vary wider around the mean of means. In which case, if it is 0.4, which is a large standard error, then it would mean that the interval ranges from here to here. So the wider the standard error, the bigger the standard error of the mean, the wider the interval around the mean. Now, if we want to make estimates that are so precise, meaning estimates that are so accurate and close to the mean of means, it means we should get a smaller standard error of the mean. If the standard error of the mean is 0.01, it would mean that these values vary very little from the mean of means, because this standard error of the mean determines the interval by which they are off, below or above the mean of means. So that is something very important to always remember. As the sample size increases, the sampling error of the mean decreases, so our estimates become more precise, closer to the truth. If the sample size is small, the sampling error of the mean is wide, therefore our estimates are getting further away from the truth. So mathematically, this is how we calculate the interval when we are doing interval estimation. It is a probability. And I know that this may cause some problems, but let me first illustrate this. We have X bar here, which is the mean, which is the statistic that we've got from the sample. Then we apply a standardized amount, standardized deviation below, which is minus x bar, or plus, which is above x bar. So we get the standard error of the mean. This is sigma sub x bar stands is the same thing as the SEM, the standard error of the mean. We multiply it by the value from the table, the Z table, which you covered under the normal distribution, as we are going through probability distributions. This value represents the interval that we want to estimate. For example, if we want to estimate an interval around this mean that covers 95% of all the values, then we are going to go to the Z table and get, this one is a two-sided alpha, and look for the value in the Z table of two-sided alpha that represents 95% or 0.95 of the area under the normal distribution curve. And for the Z value, this will be 1.96. Then we multiply it by the standard error of the mean. Then we get a standardized deviation. We subtract it from this x bar to go this side. We add it to this x bar to come this side. And then that range creates the interval around x bar. Let's do an example. Sometimes things are better seen in an example. So in this example, the mean weight of a sample of 16 boys aged 10 to 15 years is 30 kilograms with a standard deviation of 8. Calculate the 95% confidence interval around the mean. And it is telling you, use this value of Z alpha over 2, which is two-sided alpha of 1.96. Now, a caution, whenever you see questions of this nature, there is always enough information that you need to solve the problem. But there is more information than you need. Why? Because at master's level, you need to learn how to distinguish what is important from what is not important. So you can see that the mean weight of a sample of 16, so our sample size is 16. They are boys aged 10 to 15. 10 to 15 here is not going to help us solve anything. It just shows the age of these boys. But the sample size is 16. The mean weight is 30 kilograms. So x bar is 30. The standard deviation around x bar is 8. So then we have everything. So we do x bar, which is 30, plus or minus z, which is 1.96, times standard error of the mean, which is SD over root n. So once we solve this, this whole thing, the standardized deviation, now will become 3.92. So we subtract 3.92 from 30 and also add 3.92 to 30 to create an interval that is 26.08 to 33.93. You notice that 30 is just right here in the middle. So the number of steps you go below it is also equal to the same number of steps that you go above it. 30 minus 3.92, you get this, 26.08. 30 plus 3.92, you get 33.92. So, and I talked about that earlier on. Now, let's go into the interpretation. How do we interpret this interval around the point estimate? There are two ways of interpreting this. And I'm going to be a bit slow on this and make sure we get them. This is one of the areas where problems can come in hypothesis testing. So, first way of interpreting the confidence interval. Here we are using a 95% confidence interval, but it doesn't necessarily mean that it will always be 95%. It can be another interval. It can be a 99% interval, depending on the science or the subject that's being studied. So the first interpretation is, if we repeatedly take samples of the same number and we get them from the same population, reference population, using the same sampling technique, then we estimate statistics from those samples. In 95% of cases, the statistics we estimate will lie within that interval. And let's go back with that explanation to the previous slide and explain what it means. Here, we took one sample of 16 boys from a population of boys in a given area. If we go back to this same population and we take another sample of 16 boys, and we take 100 samples in total of 16 boys, in the same population using the same technique, and calculate the mean in each sample, 95% of those 100 samples, their means will range between 26.08 and 33.92. 95% of those 100 samples of the same size 16 boys aged 10 to 15 sampled from the same population. And if we measure each sample 1, what is its mean? Sample 2, what is its mean? Sample 3, what is its mean? Sample 15, sample 16, sample 17, up to sample 100. 95% of those samples, their individual means will lie between 26.08 and 33.92. That's what this confidence interval, interpretation number 1, means. Now, interpretation number 2 is that based on this particular sample only, we are 95% confident that the true population mean in the population where that sample was removed lies between 26.08 and 33.92. So let me repeat this. You can interpret the confidence interval in 2 ways. You can interpret it based on repeated samples, or you can interpret it based on only this one sample. For example, if I calculate a 95% confidence interval based on only this particular sample, then I'm only confident that if I get another sample using exactly the same technique from the same population, I'm 95% confident that the true population parameter, which the statistic from a sample is supposed to represent, lies in the range that I've estimated based on one sample. So I can't be 100% sure because I used a probability of 95%. So that is interpreting it based on one sample. The second interpretation is based on repeated sampling. If we go back to this population and take samples of the same size in the same technique, let's say whether 10 samples, 20, 100, and we measure the same statistic, which is a mean in this case, 95% of the means from those 100 samples will lie within that range. Remember that the means also vary. Some are smaller, some are bigger than the mean of means. And so it's very important to understand the interpretation of the confidence interval. Based on one sample, we are only 95% confident that the true parameter, which this sample statistic is supposed to represent, lies within that range. And we are using 95% because in health sciences, we most of the time is used 95%. But this is not the case in every science. For example, in aircraft engineering or in aeroplanes, they want to be almost 100% sure that when this plane takes off the ground, it will reach its destination. So when they are calculating their confidence interval, whether it is airworthy, they can't base it on 95% because that means 5% of the times it will be erroneous. And they can base it, for example, 99% confidence interval. So if they calculate the airworthiness of a plane, and they say this plane is airworthy, so it can fly people, and they base it on 99% confidence interval, what they are saying is that based on this test we've done on this plane, we are 99% confident that it will carry people to safely to their next destination. Or you can also say, if we repeat this test that we are doing on this plane, and we do it on similar planes, 100 planes of the same type and the same test, 99% of the statistics we get from those planes will lie within that interval. So that is the interpretation, and we take a short break, and then we return with the next phase, which is hypothesis testing.